This is the last lecture in chapter 14, which is our first of 3 chapters in equilibrium. And we've pretty much spent most of this chapter talking about the equilibrium constant K, how to calculate it straightforward using equilibrium concentrations, how to manipulate it depending on what we do with the reaction if we reverse it or multiply it by an integer. And we've also talked about Q and Le Chatelier's principle. So what we're getting into in this lecture primarily is what if you do not know the equilibrium concentrations of the substances. So the title page here, if we were to write the equilibrium expression, it would look like this, just to kind of get your brain in the gear to going through this. All right, so if we knew the equilibrium concentrations of each of these substances, finding K would be very easy, right? What if we don't know? So we're going to learn about something called ice tables. It's a whole new level of complexity in equilibrium. So it takes quite a bit of focus and practice. Alrighty, so again, just to go over what we've done so far in calculating K, let's look at a real simple, straightforward case. So if we had a question like this, where we were giving the equilibrium, essentially given the equilibrium concentrations of everything. Now in this case, we're given the moles of the substances, but we're given the volume of the flask. So remember to find molarity, right, is moles per liter. So you would have to do that simple little calculation for each of the substances and then plug those concentrations into the expression for K. So again, here's the equilibrium expression. Here are the values plugged in. And probably the most common kind of oversight is you can write the equilibrium expression and then quite often students will simply forget the exponents when they're plugging in the numbers. So be real careful. Develop a system that, makes you double check exponents. Okay, so what again, as I said, what if we only have the initial concentrations of all the reactants? How do we find equilibrium concentrations? Can we? The answer is yes. That is with our ice table. So it gets its name. It's really an acronym. I stands for the initial concentrations. C stands for the change in concentrations to reach equilibrium. And E stands for the equilibrium concentrations. And so the easiest way to do this is to write the balanced equation over your ice table. And I will show you an example. Here's the reaction we're looking at. You were given the initial concentrations and asked what are the equilibrium concentrations. So how would we go about doing that? So we haven't worked much with pressure, but remember pressure is very similar, handled very similar to concentrations, okay? All right, so step 1, remember what I stands for in the ice table. It's the initial concentrations. So you simply plug in the values they gave you, and since this is in terms of pressure, not concentration, the pressures go in, right? Done the same way. Once you have the initial amounts, this is the tricky part of ice tables and also the most important part, the change column. Now, one of the things you probably want to write down is the change, the relative values in the change, it's not a column, it's a row, come from the coefficients in the balanced reaction. So I want you to look for a minute at the relative values that are in the change row. Notice that, the obvious first, that nitrogen and oxygen have negative values, okay, and that nitrogen monoxide has a positive value. So that's a reflective of what direction the reaction moves to achieve equilibrium. So in most cases, especially in this case, you have reactants present in the beginning and no product. And that'll be the most common situation you'll see. So if you don't have any product to begin with, the only way the reaction can reach equilibrium is to shift to the right. So what's going to happen, the concentrations or pressures of the reactants will decrease, thus the negative sign. Okay, that's the change. And the concentration of products will increase. So now we've discussed that. Let me get rid of some of this stuff. Why is there a 2 in front of the change in pressure for nitrogen monoxide? Why is there a 2 there? That's reflective of the balanced chemical equation, because for every 1 nitrogen that disappears, for every 1 oxygen that disappears, we get 2 nitrogen monoxide. So you can also say it as the rate of production of nitrogen monoxide is 2 times faster than the rate of disappearance of either nitrogen or oxygen. And so the coefficients must be incorporated into this change row. This, again, is the most important part of an ice table. Now, the equilibrium row, equilibrium concentrations or pressure, you simply do the math. So treat each column as a math problem. So equilibrium pressure for nitrogen would be 0.79 minus X. For oxygen, 0.21 minus X. And for nitrogen monoxide, 0 plus 2X, of course, just 2X. And this is a little bit neater rendition of that. So now you have the equilibrium concentrations. What are you going to do with them? Now you can go and substitute these equilibrium values into the equilibrium expression. So remember what that is for this. Alrighty, so we're just going to literally pull those values in. Okay. Now, if you were to keep the equilibrium expression as it is shown here, that would be a quadratic equation, which is a pain in the patootie to solve, okay? And so, fortunately, 99% of the time, you will not be required to use the quadratic equation because there is a little trick we have to dramatically simplify the expression here for the equilibrium. So I think unless they've changed the lab, I think one of the lab questions requires you to do one problem quadratic. And the last time I looked at the ACS standardized final exam, it had a couple of equilibrium problems that required you to do quadratic. So you probably, and that's probably also a good extra credit or bonus question on my next exam. So you do want to practice using the quadratic with these type of problems, but as a lower priority than what I'm getting ready to show you, the simplifying assumption. Another thing I want to that you need to keep in mind here is if you do use the quadratic equation, remember you're going to get 2 solutions for X, okay? One will typically be negative, the other will typically be positive. The negatives make no sense. In most cases, you can't have a negative molarity, right? So remember what X represents. If you go back to the ice table, it represents a molarity or pressure in this case, but similar type thing. All right, here is the simplifying assumption, which is critically important. So here's our equilibrium expression with the values plugged in. Compare that to our simplified expression. And look at it in a minute. What has changed? You have basically neglected the X values that are added or subtracted. In some cases, they'll be subtracted or added in some problems. You have neglected the X, And when can you do that mathematically? When is it okay to neglect an x? It's okay to neglect an x if the values it's being added or subtracted to are large compared to x, right?
Right?
And when are these values large? Okay. When are these values? When will that be true? How do we know when it's okay to neglect x? Well, I'm here to tell you 99% of the problems you're going to see, it's just okay. So if you're crunched for time, it's worth taking the risk and just assuming it's okay to neglect. But so that you understand it, if you encounter it on the final exam or an extra credit problem, x is very small and can be neglected if k is small, okay? So what is k? What is k, just conceptually? It's products over reactants, right? Whoops, my handwriting has gone to poo. All right, so if k is very small, what does that mean? That means that the reaction doesn't proceed much, right? It pretty much sits there and exists mostly as reactants that don't do anything. Reaction does not form product much at all. Well, if the reaction does not form product, then these initial amounts given are not going to change much, right? The original reactants that you're given, those concentrations are not going to change much. Not if the reaction isn't going to proceed. Now, what's a small k? Check this out. That is a really small k, right? So I kind of have a rule of thumb. It's not 100% correct, but it's pretty good. That if your k value is of the order of 10 to the minus 3 or even more negative, so 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, etc., that is a very small k. The reaction won't proceed much at all, and any x's can typically be neglected when they are added or subtracted to an original concentration. Now, it's worth pointing out at this point, clearly you can't neglect the x in the numerator because then you have no problem to work out, right? Okay, there's nothing this x is subtracted or added to, so it's going to be important no matter what its value is. And you can see that by neglecting x, we got a value very close to the value that we got from the quadratic. Okay, so it's just, yeah, very small difference. The last subject we're going to talk about in chapter 14 is the relationship between thermodynamics and equilibrium. Now, I know that you all wish, as I do many times, that thermodynamics would just go away, but the kind of annoying but beautiful thing at the same time in chemistry is that there's so many linkages and relationships between all the different topics. They help explain each other, and that's the case here. So let me remind you a little bit about a couple of key concepts we learned in thermodynamics that pertain to equilibrium. Delta G, free energy. That was the term that told us whether or not a reaction is spontaneous. And if you remember, a negative value for delta G told us that the reaction was spontaneous. A positive change in free energy told us that the reaction is non-spontaneous, non-favorable. And a delta G equals 0 told us that the reaction is at equilibrium. So I'm going to remind you of a free energy graph. So where we have free energy or G, not delta G, just G on the y-axis, okay? And here's the reaction progress we're looking at. And so so delta G would be the slope at any point, right? Change in G would be looking at the slope at any point on this curve. So at the bottom, where the slope is 0, that's delta G equals 0. And we also know that the lowest energy value, because of course this is energy in the y-axis, represents equilibrium. Okay, so that's where we got the knowledge that if delta G equals 0, we are at equilibrium. and that if the change in G or delta G has a negative value, if G is decreasing, it is spontaneous. With that in mind, the relationship, and I'm not going to derive it for you, but I'm sure the derivation is in your textbook or you can find it easily if you are curious. So the relationship or formula relationship between free energy and equilibrium constant is here. Now, a reminder that this little degree sign, pronounced not, means standard conditions. And remember what standard conditions are, okay? That is, if you're talking about pressure, it's 1 atmosphere. If you're talking about molarity, it's 1 molar. So pretty constraining conditions. But R, of course, is the gas constant. And anytime we're talking in terms of energy, like we are here, we want to use the gas constant that has the energy term in it, which is 8.314 joules per mole Kelvin. And it's a logarithmic relationship with the equilibrium constant. So mathematically, if you were to plug values in, if equilibrium constant is less than 1, so if we had 1 times 10 to the minus 2, there's a fractional, right, equilibrium constant. And that we've learned that if you have a small k, that means the reactants are favored. The reaction is not progressing to product very much. So in that case, what's that saying? If k is less than 1, that means the reaction's not favorable, right? It's not going to product. Reaction is not favorable. So that fits with this because according to this mathematical equation, if k is less than 1, delta G is positive. And we also know that a positive G means non-favorable, non-spontaneous. Okay, so k less than 1 goes with G with a positive value. K greater than 1, meaning that products are favored. So if you have a large K, the reaction is proceeding to products as the chemist would want. So that means K greater than 1 is the reaction is favorable. Products are being formed. And we also know what is the value for delta G in a favorable reaction. It has a negative value. Okay, another way to say that is that reaction is spontaneous. It's favored energetically. And finally, if delta G is 0, delta G naught is 0, that is equilibrium position. And equilibrium position under standard conditions, K equals 1. So here's an example, just to kind of use this formula. All right, this problem, you're given the value for K. Okay, first thing that you should notice is K is very small, right? It's less than 1. So reactants are favored. Okay, products are not favored. So if reactants are favored, that's not an overall favorable reaction as far as the products are, right? So what mathematical value do you expect for standard free energy? I would expect it to be positive, okay, non-spontaneous if K is less than 1. So get into the habit of kind of predicting before you work a problem. So that's kind of your check to see if you didn't make a math error. Also, don't forget there is a negative sign in this equation, okay? That's commonly left out. All right, so plugging in all the values, make sure you use Kelvin and that this is a natural logarithmic function. Plug in the value for K. Now, as I speak, I see a little error here. The natural log of any value that is less than 1 is going to be a negative value. So the natural log of 1.1 times 10 to the minus 10 is minus 22.9. And so the two negatives are going to cancel each other out. So your final answer has a positive value. And see, I caught myself because going through this in the beginning, I know that with this small k value, delta G better be positive. So I knew right away this negative I had there originally is not right. As always, a lot of times you're asked to present the answer in kilojoules. So if that's the case, just make sure that you know how to convert joules to kilojoules. And I hate this. There's still several students that get mixed up how to go from joules to kilojoules or the other way. Please make sure you've got that conversion down pat. It's going to show up a lot and on the final. So delta G overall is positive, which is what we expected. The reaction is not spontaneous. And that is it for chapter 14. We're not done with equilibrium, though. We're going to move into acids and bases in equilibrium.